Hi everyone, so this is going to be the oxazolone synthesis part 2. So this is day 2 of this two-part lab. So today's goal is to continue where we left off from last time. So last time we synthesized this molecule here. This is hippuric acid. And today we're going to take this along with an aldehyde and an anhydride, and we're going to synthesize an oxazolone chromophore molecule, the one that I'm drawing right here, okay? So this is highly conjugated. It is visible under like UV light and such, so it's used in like biological studies, okay? So a little bit more specific about today's experiment. So as you'll see, the aldehyde that I've drawn here, I've included an R group. So in reality, you're going to be using a number of different aldehydes. So that's probably dependent on, it probably varies from person to person, and so that'll change how your NMRs and IRs look at the end of lab. So you might see some extra peaks that maybe your classmates don't see, or maybe you have more peaks than some other people. Okay, so don't get too worried about that when we get to it. Okay, so what I've underlined here where like those two, where the R group starts and where it ends. Okay, so keep that in mind throughout this lab. Okay, so let's move on to the mechanism. So I'm going to do a little bit of abbreviation for this to kind of like help condense space because it is kind of long. So you'll be seeing me refer to the benzene ring phenyl group as like a pH in case you don't already know that. That's what that means. Okay. So we're going to initially start out with the protonated form of the hippuric acid. And we're going to react that with this acetic anhydride. Now, in the reaction conditions, there's also sodium acetate, which can act as a base to deprotonate that carboxylic acid, and then that can do a carbonyl attack of one of the carbonyls on the acetic anhydride, and that'll afford to this intermediate. There are mechanisms out there that don't show that deprotonation step at the beginning, but this works just as well. So I've abbreviated acetic acid as a B with a lone pair, okay? So once we've generated that intermediate, you have a negative charge on an oxygen, and when you force that down, you break that carbon-oxygen bond in the acetic anhydride, and that'll afford your anhydride intermediate here, okay? And you'll notice that I've specifically indicated one proton between the nitrogen and the carbonyl carbon there. And so that's actually going to be used to help drive, that's actually required, like we actually have to remove that in order for the reaction to continue. So in order to do this next step, we have to include heat because it's not very, it doesn't like to proceed just by itself. So we'll have an electron pair from the carbonyl double bond actually abstract that proton. So essentially this is a tautomerization. So you have the proton from a carbon moving onto an oxygen, and you're changing where the double bond in the system is. Okay. Now at this point is where your actual aldehyde comes into play. Okay. So you're going to force the lone pair from the oxygen back down to reform that carbonyl double bond, and that forces that new alkene that you just formed to essentially become a lone pair that can attack the electrophilic carbon of the aldehyde, and then that is actually going to result in the oxygen receiving a negative charge and then abstracting a proton from somewhere in the system. So I've drawn BH here. That's just the protonated base that we formed at the very beginning. Okay, so if you keep track of like when your base is deprotonated and when it's protonated, you can actually like reuse them like I've shown here. Okay, so if you follow that, you'll get to this alcohol anhydride intermediate, and so we actually have to eliminate that alcohol in order to proceed with the mechanism. Okay, so in order to do that, you saw me erase it, and then I redraw back in here. But anyway, so we're gonna have the alcohol take that proton, and then the electrons in that carbon-hydrogen bond are actually going to form a double bond and force the water that you just formed, okay? And that'll get you to this next intermediate that I'm drawing here. Okay, so you'll notice that that you can have two potential stereoisomers, I guess you could say, of the where the R group is on that alkene. So you could have it also on the other side, towards the nitrogen. Now, in the case of the oxazolone, in the case of this particular compound, it tends to favor one over the other, so you don't necessarily get like a racemic mixture of either isomer. Okay. Okay, so this next step is another tautomerization. So we're going to have the carbonyl oxygen take the proton off of that amide nitrogen, and then the lone pair from that nitrogen is going to form the double bond between the carbonyl carbon and the nitrogen itself. Okay, as I've shown in this next intermediate. Okay, so the next step is to do the cyclization. So in order to do that, again, you'll either see, you can see another mechanism where they don't deprotonate first, but you're going to have the oxygen, that newly formed alcohol oxygen, attack the carbonyl carbon of the anhydride there closest to the alkene. And so you'll get to this intermediate where you have a negative charge on the oxygen. So if we force the electrons from that negatively charged oxygen down, that actually forces the carbon-oxygen bond that would form the anhydride to break, and that will generate an acetate anion as a byproduct, and that'll give you the final product here. Okay, so that's the mechanism for going from the hippuric acid to our final product. Again, there are mechanisms drawn where they don't do the deprotonation steps at the beginning, and you're just going through with an extra proton through the reaction. But either way, gets the general idea across. Okay, so a thing to note about the procedure for today's lab. So there is actually a number of different R groups, so different substituents that you can add to your product. I believe they are varied according to fume hood. There's a table on the lab manual page that'll give you all like the different substitutions and what they look like and everything. Okay, so what that means is that you're going to have different NMRs than your maybe your partner or other classmates. Okay, so you're going to see maybe a couple different NMR peaks. Shifts might be a little different. But there will be some key peaks that are either the same or similar. Okay, so one other thing that you need to do for this lab is the TLC, and you're going to be doing that in 80-20 hexane ethyl acetate mixture. So make sure to like circle your spots and everything after you've looked at them under UV light. You'll also be taking FTIR of your compound. Okay, so some of these compounds are like the NMR are going to have different peaks at different wave numbers. So keep that in mind and make sure that you know like what your substituent on your R group is. Okay. Okay, so safety concerns. So acetic anhydride is actually corrosive. So try to be careful with that as you would with other corrosives. And then essentially everything else that you encounter in this lab is an irritant. So they won't be pleasant to get on your skin or anything, but you should try to avoid that in any case, okay? So those are really the only two safety concerns that you have for this lab, and that's it for this lab preview.